All right, so we are back here. We just talked about how we can calculate our solubility when we know our solubility constant. But let's think about our solubility if we don't have pure water, right? If we don't have pure water, one of our concentrations here is going to be larger than 0 to start with, right? Essentially, right, yeah, we're adding x to those. And so now, because of that, right, we have what's called the common ion effect, right? So qualitatively, right, our KSP, right, is going to be greater in pure water, right? It's going to be larger in pure water compared to, or actually, our KSP does not change, but the amount, the amount of solid that is going to dissolve is going to be greater in pure water compared to unpure. Okay, so something that already has something in there, right? If we have multiple things that maybe one of them's going to dissolve, or one of them's going to precipitate out of solution first, the greater KSP, right? If KSP, whichever one is greater, so KSP1 versus KSP2, KSP1 is going to, or the smaller KSP is going to precipitate first, okay? So smaller KSP will precipitate first, okay? So that's just qualitatively, but quantitatively, we can actually calculate how much this common ion effect is going to change our solubility, okay? So let's take our solubility, that same AgCl, but now let's have in a 0.1 molar NaCl solution, right? So we're going to create our rice table or ice table, right? Our reaction, of course, is AgCl dissolving, and so it's going to be Ag plus aqueous and Cl minus aqueous. This starts as a solid, so we don't really care about our the ice for that, but we start out at 0 for Ag plus, and our Cl minus is actually going to start out at 0.1 molar, right? Our Cl minus from our NaCl, this is completely soluble because our Na plus is totally soluble, so it's going to completely dissolve. So we have 0.1 molar Cl minus there, right? So our initial value for chloride ion concentration is 0.1 molar. But when we add in our AgCl, right, we're going to add X and we're going to add X here. So overall, we're going to have X as our equilibrium for Ag plus. We're going to have 0.1 plus X for a concentration of Cl minus. Then we write our equilibrium expression, which is, of course, Ag plus concentration times Cl minus concentration. We're going to plug in our numbers, so we know Ksp from above is 1.8 times 10 to the minus 10th. And that equals, well, X times 0.1 plus X. And then we realize, like, ooh, that's kind of gross. That's going to be a quadratic, and that does not seem very nice, okay? Solving that, the AP test will not ask us to solve a quadratic, okay? But we can solve it if we know the quadratic equation, we know how to calculate it, we can solve it quantitatively, but we can also make a little bit of an assumption. Is our chlorine concentration going to change a whole lot? Well, let's remember, up above, right? Up above, we said, well, in 1 liter, our concentration is going to be 1.3 times 10 to the minus fifth. 10 to the minus fifth versus 0.1, that's 10 to the minus 1. That's 4 orders of magnitude difference. So that's probably not going to change a whole lot. So we're going to make an assumption where we can kind of just ignore this plus x here. And then this is much easier to solve, because now we can say, well, x equals 2 times 10 to the minus ninth molar, right? So really, yeah, we're going to be able to get a little bit of AgCl, and it's going to change a tiny bit of that Cl minus, but it's small enough that we're not, our accuracy is not going to be enough to measure that difference, okay? So that's why we can say, yes, okay, we can make that assumption, okay? So quantitatively, right, we can measure and we can calculate exactly what that solubility will be in when we have that common ion effect. We have a couple more common ion effects that we want to, or a couple more effects with our solubility that we want to talk about. pH and solubility. What if rather than AgCl, I was using AgOH? All right, this is a solid as well. We're going to have an equilibrium where we're going to form Ag plus, aqueous, and OH minus, aqueous. Now, if we remember, oh wait, OH minus, this is of course going to have to do with our acid bases as well. Okay, so pH is actually going to affect our solubility because we have this reaction and equilibrium as well. This equilibrium, HOH or H2O, right? This equilibrium over here, we are going to talk about next unit, okay? Next unit is all about our acid-base equilibrium, okay? But if we have a more acidic solution, right? We bring that pH down. That means our H plus concentration is going to increase. So we make this the fat guy. This reaction is going to want to move towards making more H2O. So our OH minus concentration is going to decrease. If we decrease that OH minus concentration, we need to move this way, and we'll actually be able to dissolve more of our AgOH because we lost some of that OH minus, okay? So we're going to talk more about this next unit, but this is one effect, something that will change, right? Our pH will change our solubility. It'll change how much of our solid is going to be able to go into solution based on the pH there, okay? If we make, of course, if we make it more basic, right, we add more OH minus, it's not going to want to go that way. It's going to actually want to go more towards the solid, and we're going to only be able to, we're going to be able to dissolve a smaller amount of our AgOH, okay? The last piece with this unit, our energy of dissolution, right? Our energy we've talked about last unit, but really what this is saying is when we talk about our solubility, things get a little bit complicated. And the energy and how much things will dissolve is going to kind of be difficult for us to measure and predict based on the energy, okay? So something may be favorable, right? It may have a delta H where it releases energy. If it releases that energy, hey, that's good, but there's another thing that we're going to talk about in Unit 9, so our last unit, that has to do with our free energy, and it has to do with the spontaneity of these processes, okay? So essentially, energy of dissolution, don't worry too much yet. But really what it says is we can't predict. Okay, so that's all for Unit 7. There's all of our notes. Let's go and do some work with it.